And we'll go from current slide. But before we start today, there is an announcement, and probably others, but this is the only one I had time to print off yesterday. Several colleges, universities in the area have sponsored programs called the Noyce Scholarships. They typically, I think they're all related to trying to encourage good, qualified people, meaning good people in science and math, to consider teaching science and math, because we have a terrible shortage of science and math teachers in K-12. So the Noyce Scholarships try to encourage, they welcome all comers, especially those who are in science and mathematics areas, to come and do a summer internship with them. They pay well, they provide room and board, they provide transportation, they pay for transportation there and back usually one time. Here's Thomas. And it's a great experience. We've had several students participate, and they come away very enthused. Patel's here, okay. Good deal. All right. So please, if you're in any of those areas and you have considering doing a few things, you'll need to find the details. UAB had a program. UA had a program. They're like 3 to 5 year grants, and whether they got renewed or not, I'm not sure. But just recently, Alabama A&M University got a grant for the Noyce Scholarship. They're National Science Foundation grants, so they cover really well, and you learn a whole lot. And it's fun, okay? So if you're at all interested, check your email, because you got this email just like I did. And on there, there's a link that you can go to and find out all the information you can possibly want to know about it, okay? I don't know when the deadline is. They don't say, but it's on here. Please consider it. It's a nice, you can make a little bit of money this summer while you're learning something. See, here we make you pay to learn something. There, they pay you to learn something. So it's a pretty good deal. So look for that. All right. Any questions before we get started on anything we've done so far? I know a few people came in since I last asked this question. Does anyone not get a quiz? All of you got the quiz. Okay, good. We finished 1.6, and that was the quiz point. We're starting today on 1.7. Chapter 1 is still functions and their graphs, and 1.7 is transformations of functions. All right. I'm going to talk about several types of transformations, where you can change functions. Remember, at the end of 6, we found the parent functions, which are the simplest, most direct of most of the functions. And now we're going to do various things to those. First, we're going to start with vertical and horizontal shifts, okay? Vertical shifts, move it up or down. Horizontal shifts, left to right, and combinations of those. We'll also do reflections across the y-axis, across the x-axis. Those are reflections to sketch the graphs of functions. And then these are all what they call rigid transformations. There are non-rigid transformations. You see, in these two, the function keeps its shape, doesn't change. Okay, it changes where it's located on the page, but it doesn't change its shape. It's rigid. The non-rigid do change their shape slightly. They stretch or they shrink. That kind of horizontal or vertical, those are the non-rigid transformations we'll be talking about. All right, so if we start with those shifting graphs, okay? Many functions have graphs that are transformations of parent graphs. For instance, if you recall, here's your parent function. We called it the squaring function. Some of you called it the quadratic function. The simplest one is f of x equal x squared. Okay? That's how it always looks. 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. That's how this one looks. Okay? Keeps on going. Now, notice this one. H of x is x squared plus 2. How does this differ from that? Yes, you've added 2 to the function value. Okay? Well, what is the f? Someone remind me of that? F of x is y. Why not? Okay? Dion, let me get you here. There you are. Okay. Good deal. Anyone else come in since I called roll? Okay? So since you're adding it to the function value, which is the y value, that means you're moving up 2 spaces on y. And look at this. From 0, 0, 0 on y here, to 0, 2. Where's the 2 on y? 1, 1 here, 1, 3 here. Negative 1, 1 here, negative 1, 3 there. Okay? And if you could see it, 2, 4, that would be 2, 6. Everything is just shifted up 2 units. Vertical shift. By shifting the graph of f of x equal x squared up 2 units is shown here. Pretty simple, huh? What would a minus 2 have done? Move it down 2 spaces, okay? So those are your vertical shifts. When you're adding or subtracting to the function value, to the parent function, you go up or down however many places it says, okay? So in function notation, h and f are related as follows. H of x, which is x squared plus 2, x squared is f of x plus 2. So again, it's a shift up. This is y plus 2. Take the y value up 2 spaces for your new y value here. Similarly, you can obtain, okay, should have been a new slide here. What if you were adding or subtracting from the x value? What do you reckon that's going to do? You add or subtract from the y value, you move up or down. How about adding or subtracting from the x value? Side to side. Okay? Here's something to keep in mind. X's are always backwards. I don't know why, they're always backwards. Okay? And x minus 2, guess what way it's going to go? Right, not left. Right. Okay? F of x minus 2 would go down, but x minus 2 goes right. The x's are always backwards from what you would think they would be. That's shifting the graph to the right 2 units. And here's part of the reason, okay? Your f of x is x squared. It's at 0, 0 right there. Same one we had before, okay? Now, when x is equal to 2, this becomes 0. So your g of x is going to be 0. When x is 2, g of x is 0. So sure enough, it's shifted 2 spaces to the right, even though it's a minus sign there. Okay? If this had been x plus 2, 2 spaces to the left, because it would take negative 2 plus 2 to make 0. So sure enough, whatever the x's are doing, it's always backwards from what you would expect the y to be doing. Okay? Does that kind of make sense? In a weird kind of way. If you're adding or subtracting to the y value, go up or down. Adding or subtracting to the x value, then go left or right. I said no, right or left? Left or right. I said it right the first time. Okay? So, that's a horizontal shift. Now notice also, the shape of the graph did not change. It's exactly the same as a rigid transformation. Okay? Make sense? I believe we're getting a little rain. It's been, several days since we've had rain, so we're really in a drought. Okay. So in this case, the function g and f have the following relationship. G of x is x minus 2 squared. Well, that's the same as f of x minus 2. Okay? Yeah, okay. Because what's in here was what was squared, so it's x minus 2. F is a squaring function. That is a right shift. Remember, anything dealing with the x goes in the opposite direction. So the following list summarizes this discussion of horizontal and vertical shifts. Only these are vertical and horizontal shifts. Let's see. You tell me, what's h of x in this first one here? What kind of shift is it? Or is it? H of x equal f of x plus c. C now is a positive number. Let C be a positive number. So what your h of x be compared to f? Earth to class, and then please. Okay. Yes, that would be going up C units. Okay. What would H of x equal F of x minus CD? It's gone down C units. Okay. How about H of x equal F of x minus C? Right C units, and H of x equal F of x plus C. Left C units. Perfect. Y'all got it. Any questions on that? Okay. Now, some graphs can be obtained from combinations of vertical and horizontal shifts, and example 1b is going to do one of those. Did we already do it? I think we were supposed to have, because I think they skip it. Nope, there it is. They haven't done it yet. Okay. So, oh, there it is. I see this slide at the bottom. Okay. Can be obtained from combination of vertical and horizontal shifts. Now, vertical and horizontal shifts generate what they call a family of functions. Okay. Each with the same shape but different location in the plane. Now, is this just blah, blah, blah stuff that, oh, let's make them think of this. Let's make them remember this. No, actually, I'm teaching a differential equations course, and hopefully some of you will continue that far, and we talk about families of functions all the time. Yeah, without knowledge of this, that would make a lot of sense. So this is something that is done and used. All right, so here we have a graph. It says use the graph of f of x equal x cubed to sketch the graph of each of the following functions. All right, so let's do, whoa, I meant to change my color first. Okay, we'll assume this is the coordinate graphs, and we'll just tick off a few points. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. We don't need that many. 1, 2, 3, 4, 5, 6, 7, 8. And negative 1, 2, 3, 4. Okay, we won't need them all, but there we go. So let's start with this function. F of x equal x cubed. How does that look? What are some points on that graph? F of x equal x cubed. Give me an x. 2. 2 cubed is 8. So we're over here at 2. 1, 2, 3, 4, 5, 6, 7, 8. We just barely made it. There we are, right up there. Okay, give me another x. 1. 1 cubed is? Say again? 1. Okay. So there we have a second point. Give me another x.
4.
Okay. Off scale. 4 cubed is 64, I think, or something like that. No, that's 4. Yeah, 64. Negative 1. Okay, what's negative 1 cubed? Negative 1. Perfect. Another one? Easy one? 0 cubed would be what? 0. Got it. The negative 2 would be off scale down here, so it's going to be something coming, I can't draw well, like this and then like that. Something that looks like that. Not so wavy in there, but whatever. Okay. Now, with that, let's first do g of x. What color you want g of x to be? You pick it.
Green.
Green for g. Okay, got it. Light or dark?
Dark.
Dark. Okay. So this is going to be our green graph. What is happening to that from what your f of x was? Say again? Going what? Up. This one is going down. The f of x follows the rule. If it's a -1, it goes down 1. Okay? So every one of these points is going to go down 1. For the same x, go down 1. So this will go down to here. This will go down to here. This will go down to there. This will go down to here. And the next one we couldn't see anyway. So it's somewhere down there. All right, so this is what, oops, I don't draw well, sorry. It's not that wavy, okay, but that's what it looks like. Same shape, believe it or not, rigid, but it's a vertical shift downward. Do you see that? Okay. Now these two lines get really, really, really close together because there's not much difference going up there. Biggest difference is right in here. Right. Z? Okay. Now Q, I'm sorry. I had a Z last term. Okay. Kind of wet out there, isn't it? And getting worse, it sounds like. And by the way, folks, the temperature is dropping just about all day today. It gets down into the 50s rather than the 60s like it was coming in this morning. In February, early February. All right. So there's g of x. Okay? Now, if you can read it, what in the world is going on with h of x? You tell me. Okay, move to the left. How many?
One time.
Second?
One.
Huh? Okay, which is the...
Oh, sorry, it's one.
Okay, which is the horizontal? X or Y?
X.
X. So what is X being changed by? 2.
2.
So left 2.
Yes.
And?
One up.
1 up. Okay, so every point is going to go left 2 and up 1. Okay, just don't say yours. Okay, so 0, 0. Go back to the original, by the way. 0, 0. Go left 2 and up 1. Whoa, wait, I forgot to ask. What color is H? Say again? Blue? Okay. Light or dark? Light? Is that what you said, huh? Dark. Okay. Okay, dark blue. So this is our H. I don't hear well, so please speak up. Okay? So that's going to go left 2 and up 1. So there's the first point. Okay? That was the origin. This one would be left 2 and up 1. That would be right there. This one would go left 2 and up 1. That would be right here. This one left 2 and up 1. That's off scale. Okay? Whoops, up, left 2 and up 1. So it's on the y-axis, but we can't get to it. And the one down here, left 2 and up 1, still off scale, but it would be somewhere around here. And this would be, whoops, going up there. Approaching the y-axis, and somewhere up there it's going to cross it. Okay, again, same shape as your original, kind of. Okay, I got these spaced out too far. Just a rigid transformation, left 2 and up 1 from the original parent function. Does that make sense? Those are your rigid translations. Okay? Shifts, they call them. Okay? Let's clear my scratch out of the way and see what they do. All right. Relative to the graph, the gray graph here of f of x equal x cubed, notice they have a lot more flatness in it than I did. The first one here, x cubed minus 1, shifts down 1. So every point goes down 1. Every value goes down 1. Okay, they don't show any more than those. And there's the shape of it. So here's your g of x, which we did in green. They did this way. Can I get your name, please? Mayfield, got it. Okay. Okay. Kendria. Okay, good deal. Anyone else come in that I didn't see? I didn't call your name. Okay. All right. All right, so there's your A one that we did in green. They are doing in dark white. Okay. Or black, I guess you would say, as opposed to gray. Any questions on that one? Just down 1. The other one is a combination, a left shift 2 units from here. Remember, everything to do with x is backwards. Even though it's a plus 2, you shift 2 left. But vertically, you go up 1. Okay. So this one, again, goes left 2 and up 1. This one goes left 2 and up 1. This one goes left 2 and up 1, right there. So every one of them, 2 to the left, up 1. You have the same curve, it's just shifted both horizontally and vertically, but same. It's a rigid transformation. Any questions? Okay. So in example 1b, the one we just did, you obtain the same result when the vertical shift precedes the horizontal shift. So you could have done up 1 and left 2. That would have worked just the same. Doesn't matter the order. Or when the horizontal shift precedes the vertical shift, left 2 and up 1. Works the same way. A few of the ones we'll do in the future don't, it kind of matters a little bit. You have to sort of pay attention. It's sort of like line dancing. If you don't do it in the right order, you bump into the person next to you, right? Okay, or something like that. I don't do line dancing, by the way. Okay. So, that was example 1. By the way, there is a checkpoint. Please do the checkpoints. They can be found at larsonprecalculus.com if you have any problems with them. Okay? Now we're going to start reflecting on graphs. Okay. Another common type of transformation is called a reflection. Okay? For instance, if you consider the x-axis to be a mirror, then what is this doing? H of x is minus x squared. What is that doing? For any value y here that you had for x squared, what does this do? Negates it. Okay? So now rather than a positive number, it becomes a negative number. So that is exactly a reflection across the x-axis. And like they say, imagine the x-axis is a mirror. What was up here is now down there. Just an exact reflection downward. Okay? It's an exact reflection of your parent function, which is f of x equal x squared. Make sense? Again, rigid, no change of shape, just change of, the other was change of position, this is change of direction, but exactly the same shape. Okay? Make sense? All right. So here is your little blurb on how to do it. Reflections in the coordinate axis of a graph are represented as follows. Reflection in the x-axis, you're changing the y value, so you negate the y. Okay? A reflection across the y-axis, you're changing the x value. Y values are staying the same, x values are changing, so then you negate the x. Okay? Now what does that look a lot like? This was a test for what? We did earlier. What did we do if we were trying to determine?
It's going to be on this display.
Yeah. Even or odd functions. That's exactly what this is a test for. If when you do this, you get exactly f of h of x, then you have an even function. It's doing the same thing on either side. If you do that and get this, okay, then you it's an odd function. Okay, that means you reflected it across the origin. So that's, if that looked familiar, that's what it was. Okay. Oh, my nose is itching. We must be going to have company. Okay. Y'all need that a little bit longer. Okay, everybody got it? All right, so here's example 2. Here's a graph of a function. F of x is equal to x to the 4th. What does that look a lot like, the graph? Say again?
Parabola.
Yes, it looks like a parabola. It's not quite. It's very similar. Here's the differences. Flatter near the origin, steeper on the sides. Okay? Flatter near the origin, steeper on the sides. But there's the function, f of x equal to x to the 4th. Now, before we go any further, even, odd, or neither?
Even.
Even! Same thing happening on the right as happening on the left, okay? That's an even function. That's not what we're doing now. Okay. Now, do you think you could do a reflection across the y-axis? You could, but it looked just like that, wouldn't it? Okay, because it's an even function. No change there. What would happen if you reflected across the x-axis? It flips over here, right? Exactly like that, but flipping there. What would be the g of x that would cause that?
Negative.
Negative x 4th, exactly. Okay? So, I think that's what they're going to do next, isn't it? You tell me what this one would be. What's going on with this one? Say again?
We have to tell from the last one.
Yeah, from the one we saw before, the alpha of x.
It reflected and
Reflected first, so minus alpha of x, or minus x to the fourth, and then
Move up.
up 2, plus 2. Minus x to the fourth, plus 2. Now, you can't, you can think of doing it this way, but if you've done the plus 2 first, then try to reflect that across the x-axis, that doesn't work out well. That would have put it up here, and that would have reflected down here. That's not what we do. You reflect it first, exactly like you said, minus x to the fourth plus 2. So sometimes the order does matter, okay? With horizontal and vertical shifts, doesn't matter. But with these reflections and stuff, you have to be careful. How about h? Okay, so this will be, it says each of the grasses, write an equation for each function. So you write an equation for this. Tell me what it is. Let me get my color back. Field ported peak. That'd be, yeah, y is equal to g of x, which would be equal to minus x to the fourth. There's your reflection, plus 2. Perfect. Okay, what's happened to this baby?
It's moved on. So you
Okay, you reflected first, and then you scooted over to the right. I mean, 3 places. So what would that seem to be? Y is equal to h of x, which is equal to what? Minus x what? Minus 3 to the fourth. Perfect, okay? Yeah. If you did the x to the fourth first and minus 3, you'd have been lowering it. Okay, so you have to do the minus 3 since that's a horizontal. It's on the x-axis moving it this way here. That's a minus 3 because you're going to the right, backwards, remember it's x, and then the regular function. So you negate and then and shift. So both of those. Now, in this one, you could have said, well, yeah, we could shift it first up here and then reflect. Yeah, that would work either way. This one wouldn't. You have to be careful with that kind. But this one, that was perfectly fine. Make sense? So you've written the equations of both of those. Let's see how the slide set did. Okay, the graph of G is a reflection followed by an upward shift. This, the order matters, and that would be reflection of minus x to the fourth, then your plus 2. Exactly like you got it. Good deal. Okay, the next one is a horizontal shift 3 units to the right, followed by, you could have reflected first and then shifted. It didn't matter on this, but this works too. Horizontal shift followed by reflection, and that gave you minus an x minus 3 to the fourth. Now the reason they said it was the shift first, usually you do parentheses first, so you subtract the 3 first, shift it to the right 3, then reflect. But it doesn't matter on this one. Y'all got it right both ways. Any questions? Does that make sense? All right. I guess I ought to close the door to keep from bothering people up and down the hall. I should have thought of that earlier, but I didn't care earlier. Okay. Any questions on that? Translations, shifts, or reflections? All right. When sketching graphs of functions involving a square root, remember you must restrict the domain to exclude negative numbers inside the radicals. Okay? Got to. You can't take the square root of a negative number. For instance, here are the domains of some functions. g of x minus the square root of alpha, the square root of x. What would be the domain of that function? What values can x take on? 0 and positive. Still, whatever x is, 0 and positive. What's the range of that function? Normally the square root function looks like this, but this does what? Reflects it. So now they're everything from the range 0 to minus infinity, okay? Because this is a reflection. Doesn't change the domain. Domain stays greater than or equal to 0. How about this one, though? The square root of negative x. Do I hear you screaming and say, no, you can't do that. You can't take the square root of a negative number. I didn't hear anyone scream that, did I? Okay. Now, can you do this? As long as x is what? Negative. Because you take the negative of the negative, you got a positive. And you can take the square root of a positive number. So here your x, what's your domain here? All negative numbers from 0 to negative infinity. Okay? All x is less than or equal to 0. How about this one? Oh, and what's the range of this one? I don't have to cover that. It's not a range. What's the range of this one? Yeah, positive, because you see this is principal square root is always going to be positive. The trouble is it'll be numbers over here. That graph will look like this, okay, on the left side. Okay, what's the domain of this one? Second? Positive numbers? That certainly will work, but there's more than that. Say again?
Would it be like 2?
Okay. Here's how I do it. Now, they show you the answer, but here's how I do it. What's the rule? Everything under the square root symbol has to be positive, greater than or equal to 0. So I say that. X plus 2 is greater than or equal to 0. Now solve for x. What would we do? Subtract 2 from both sides, and that would give us x is greater than or equal to negative 2. And sure enough, that's what we got. Okay? X greater than or equal to negative 2. Okay? What's the range of this one? All numbers greater than or less than or equal to 0. Okay? They didn't ask you that, I asked you that. Okay, no extra charge there. So, do you see how that works? If you have a limitation, it applies to what's inside. Here, x has to be greater than or equal to 0. Here, negative x has to be greater than or equal to 0. That means if you multiply or divide by negative 1, that makes it less than or equal to 0. And here, x plus 2 has to be greater than or equal to 0. Anything under that has to be greater than or equal to 0. When you subtract 2 from both sides, you get x greater than or equal to negative 2. Because you see, a negative 2 will work because negative 2 plus 2 is 0. Yeah, you can take the square root of 0. 0. Okay. Good deal. Any questions?
Yes.
Yes?
Okay,
Yes.
so but the range, when it's the negative on the outside, is
Yeah.
going to be positive, so it's going to be basically the opposite.
Yeah. For this one, if there's a negative on the outside, that flips. Okay, now square root of x, remember, looks like that. Half a sleeping parabola, the upper half. When you negate that, you flip it over the x-axis. So now it's all values of y less than or equal to 0. Okay? This one, even though your x is moved over here, that's a reflection across the y-axis, but the y values are still positive because this is only positive values. This one is a horizontal shift 2 units to the left, okay? But then you go this way because, no, I'm sorry, you go this way because normally it would be like this. The negation flips across the y-axis. So that changes your range, okay? This changes the domain. That changes the range. Okay. Good question. Any others? Good question. All right. All right. They left off example 3. Shame on them. Okay. So let's go back and find some place to do example 3. I think this will probably be our best bet. Compare the graph of each function with the graph of f of x is equal to square root of x. Okay? Going to have to start by you telling me how to plot that graph. Okay? Let's tick off some points here. 1, 2, 3, 4, 5, 6, 7, 8. We won't need that many. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Negative. Oh, that's negative 1, 3, 4, 5, 6, 7, 8. Okay. We're going to plot f of x equal square root of x. Give me an x. 1. Okay. What will your f be? Okay. All right. Oh, yeah. 1, 1. Perfect. Next. 0. What will the x, y be? 0. Excellent. Next. Don't do 2. Your first inclination.
Negative 1.
No, you can't do negative 1, can you?
No.
No. Huh? Okay. If you did 2, it'd be 1.414. Yeah, okay. I'm not going to plot it. Give me a better x to put in there other than 2. 4. I love it. Okay. 4, 1, 2, 3, 4. What would that be? Second, 2. Perfect. Okay. And if we had enough spaces out there, 4, 5, 6, 7, 8, 9. Okay. Next one would be 9, 3. Okay. Here's 3 up here. So there that would be. So here's our parent function, the square root function. Something like that. Maybe a little flatter here, not as wavy there. Whatever. Okay. Now that's our initial. And you're going to need to give me a color for A. Give me a color. Purple. All right. Okay. And purple will be g of x is equal to negative the square root of x. What is that doing? Across the x-axis. You're absolutely right. 0, 0 will still be right there, but then 1, 1 will now be a 1, negative 1, reflecting across the x-axis. 4, 2 would be 4, negative 2, right there. And 3, or 9, 3 would be reflected across there to be 9, negative 3. Okay? So there, that would be. Okay. Makes a complete parabola. Okay, sleeping parabola, by the way. Okay, good deal. That was your A. Give me a color for B.
Red.
Second? Red, okay. All right. B, the red one, will be h of x is equal to the square root of negative x. Wait a minute. Can you do that? Can you take square roots of negative numbers? No. But what your x have to be? Negative. Now negative and negative is positive, so you can take the square root of it. So where would these be? What would this be? Compared to f. Reflection across the y-axis. So you just take everything here, reflect it across. So your 0, 0 is still 0, 0, but here 1, 1 becomes a negative 1, 1. And a 4, 2 becomes a negative 4, 2. Okay? And let's just imagine there was a 9 out here, negative 9, or 9, 3 becomes a negative 9, 3. Somewhere right about there. Okay? So now your half a parabola is like that. There's your h of x. You see? Okay? Notice your domain has shifted because of that negative inside the radical. Okay. I need a color for C. What color is the C? No, oh, never mind. Okay. Second? Green? Okay. I'm going to go with dark green then. Okay? Thank you. Getting hung up. Okay, so your C one here is K of x is equal to minus the square root of x plus 2. Uh-oh, what in the world is happening here, folks?
It's gonna reflect
Think
on,
now, always think back to your F. What's happening first?
reflect on the X.
Okay, reflecting across the x-axis, that's what the minus sign is doing.
And then plus 2 gonna move
Move up.
to
Okay, you're pointing right, what did you say?
left.
Ah,
This moves here.
left, okay, left 2, okay? So, we're going to take this graph, go left 2, and then reflect across the x-axis. So the left 2 would have taken us over to here, but then the minus sign takes us down here. So that would be 0, 0. This point here goes left 2 and reflects across the x-axis, somewhere down there. This point goes left 2 and reflects across the x-axis. That would be somewhere like right there. And this point here goes left 2 and reflects across the x-axis, somewhere like there. So here is your graph. Okay? No, that's not right. It didn't go down far enough. Sorry, let me get that straightened out a little bit. It's not a big deal, but I was not going enough places down. Okay. Okay. This left 2 and down 2. It's down there. Okay. And this is left 2 and down 3 right there. Okay. That's a little bit better. Something like that. Same shape. Rigid transformation, however, moved all over the thing. This one's reflected across the y-axis, reflected across the x-axis, shifted to and reflected across the x-axis. But it's the same shape everywhere. Does that make sense? Rigid transformations. All right. So yeah. And that leads back to your domains and ranges. Here's the domain greater than or equal to 0, range greater than or equal to 0. Here the domain is less than or equal to 0, the range is greater than or equal to 0. Here the domain greater than or equal to 0, range less than or equal to 0. Here domain greater than or equal to -2, we did that one, and the range is less than or equal to 0. Make sense? Domains, range. All right, that was your reflections and shifts. There is a checkpoint. Please do the checkpoints. That probably will require some review. Okay, so let's see. Let's move on to, we already did reflecting graphs, non-rigid transformations. Let me take out my white so I don't go too far over. Okay. All right. Non-rigid transformations. These would be sort of flexible, fluid transformations, you might say, but still have to follow rules. Okay. Horizontal shifts, vertical shifts, reflections are rigid transformations because the basic shape of the graph is unchanged. These transformations change only the position of the graph in the coordinate plane. Move it up, move it down, move it up and down, I mean right or left, up or down, and then also reflect. But the shape stays the same. The non-rigid transformations are those that cause a distortion, a change in the shape of the original graph. And here are the two changes of shape we'll do. Stretching, stretching, shrinking, or shrinking, horizontally and vertically. Okay. So, for instance, a non-rigid transformation of the graph, y is equal to f of x, is represented by g of x is equal to c times f of x. So this time, for every x value, you find the f of x, but then you multiply it by c, which is if c is a large number, greater than 1, bless you, then it stretches vertically. If it's a small number, it shrinks vertically, a number less than 1, okay, between 0 and 1. Vertical stretch, if c is greater than 1, and a vertical shrink, you see, is between 0 and 1. We don't usually multiply by zeros, right? That loses all value, meaning of your function whatsoever. Okay. Another non-rigid transformation is when the x, this is multiplying by the y by a constant. If you multiply the x by a constant, same f, but now it's f of cx, where the transformation. Now, guess what? What happens if c is greater than 1? What you reckon is going to happen to that?
It's gonna stretch.
Second?
It's gonna stretch.
I can't hear.
It's gonna stretch. But it's
Okay,
gonna,
but this is x, isn't it?
yeah, horizontal.
Everything's backwards. Everything's backwards. It's a horizontal shrink. Okay, remember, anything dealing with x is backwards. Whereas a large C would make a vertical stretch, a large C will make a horizontal shrink. And when C is between 0 and 1, it's a horizontal stretch, backwards. Everything dealing with the x is backwards. Horizontal is backwards from what you would think the vertical would be doing. Okay. And you can sort of see it if you think too deeply, but you usually get a headache doing that, so don't. Okay, never mind. All right, so here's example 4. Compare the graph of each function with f of x is equal. Oh, what do these bars mean? Absolute value of x. Can anyone remember what the absolute value of x looks like? I'm going to go back to black for this one. Okay. Okay. Tell me what f of x being the absolute value of x looks like. It's what? A v, exactly. In fact, if you think about it, here's the definition of absolute value of x. Okay? It's a piecewise defined function. It's equal to x when x is greater than or equal to 0, and it's equal to minus x when x is less than 0. See, make sure I say that right. Yes. Okay? So over here, right of the origin, it's the identity function. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. Identity function, right? Like that. On the other side, identity function would continue going like this, right? But here you negate that, and you make it the other diagonal. So yeah, it's a V-shaped function. That's what absolute value of x looks like. Okay? Now, what color you want H to be? Got to get the important questions first. What color you want H to be? Say again? Red? Is that what you said? Okay. We'll go with red. Okay? And what are you doing with this? And by the way, I should have put the points on here. Let me back up and do that. Okay? Okay, 0, 0, 1, 1. Oh, I thought I changed it. Okay. Okay. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, or negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, negative 5, 5, negative 6, 6, blah, blah, blah. Okay. All right. So now we'll go and change to red. All right. So what happens to 0, 0? Stays 0, 0, okay? Because you multiply absolute value of 0, which is 0, by 3, you still get 0. What happens to 1? When x equals 1, h of x is this, that becomes 3. So it stretches up to here. And same with negative 1, it stretches up to here. Okay? And 2 was 2, it stretches up to 6. That would be 3, 4, 5, 6, up to there. And negative 2 stretches up to 6 as well. Okay? 3 stretches to 9, 7, 8, 9, up to here. Okay? If I can find it. Ooh, red on red. That's tough to see, isn't it? Okay? And over here, 3 will be 9, 2. Okay, who chose red, huh? Okay. And this is what happens to it. Okay. I don't know y'all grew up with electronic toys. I don't think we ever had one, but I remember seeing these things. Little things that you pulled the string, and the puppet came up like this, right? Okay, you saw it. You've read about it in your history books. Okay. Okay. Well, this is what's happening here. You're pulling the string up, and you pull the arms straighter up. So they're like this. Pull up. Yeah. Okay. That's what's happening. Vertical stretch. Okay. How about G of X? What color you want that to be? Let me, before I do that, that was the H of X. Now I'll do G of X. What is G? Green. I thought you were going to say that. Okay. We aren't too predictable, are we? Okay. So what do we do here? 0, 0 is still 0, 0 because 1/3 of 0 is 0. 1, 1 is 1 1/3. You take 1/3 of your value of the black graph. Okay? 1/3 of this one. Here would be 2/3. Okay? Still less than 1. 2/3 and 2/3. 1/3 of 3 would be 1. 1. Okay? I'm trying to get them in the right place. Okay? 1/3 of 4 would be 4/3. Okay? 4/3. Okay? These aren't plotting out too well. 5 would be 5/3 or 1 2/3. 1 2/3. I'm getting off a little bit. 6 would be 2. Okay? So in other words, here's your absolute value here. This is the elephant set on it. Okay? This is a shrink. All these values shrunk by 1/3. Honey, I shrunk the points. Okay, no. What's that? You do remember them, okay? All right. So it's a vertical shrink because you're doing 1/3 times the absolute value of the other. All right. Does that make sense? That was example 4. I have a feeling. Oh, wait, that's right. They're doing these. Let me back off. Can I erase my mess and see how they did it? Okay. All right, so here's how they did it. Here is the original function, alpha of x equals absolute value of x. That's the identity function to the right, the opposite identity function to the left. Okay, V-shaped function. 3 times each of those values, 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6. Okay, so every one of these is stretched by 3, vertical stretch. So your 3 times output value will be a steeper V. Okay, all right, make sense? And then G would be only 1/3 of the value. So your original function, absolute value of x, now each of these values is 1/3. 1/3 of 1, 1/3 of 2, which is 2/3. 1/3 of 3 would be 1. Same thing over here, 1/3, 2/3, and 1. Okay. The alpha set on. Okay. Make sense? Yay or nay? Okay. So that was example 4. Okay. And that's all she wrote. So let's go back and do example 5. Let me get my pen back to black. Okay. And by the way, this one says, see LarsonPrecalculus.com for an interactive version of this type of example. So if you're not satisfied with my explanation of it, or you just like to see a little bit fuller, go to LarsonPrecalculus.com and you can see and hear him talk about it. I think the author does it interactively. Okay. So, whoa, look at this one. Here's not exactly a parent function, but it's the one we're starting with. I'm going to put it up here. F of x, whoa, let me get my pen back. I am back. Oh, never mind. Okay. F of x is equal to 2 minus x squared. Ooh, boy. No, that's x cubed. I can't read. 2 minus x cubed. All right. We're going to need some work in figuring out what in the world this one's going to do. Okay. There's my coordinate axes. Let's do, bless you, 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7. Not going to need that many. 2, 3, 4, 5. 1, 2, 3, 6, 7, 8. Okay. Something like that. Whoa. I didn't do that. It just popped up there. Okay. What does that function look like anyway? Do we need to do it in steps, or can you figure it out already?
It looks like it's gonna reflect on the
Okay. Mentally picture your cubic function that we started with. Remember, it started down here, smoothed out here, and went up steep, right? That's the cubic function. Then negating that is going to have it starting here, flattening out here, and going down. Okay? And then adding 2 to that is going to move it up here, so it's going this way here and that way there. You buy that? Okay. So we'll start at 2, and then we'll go down 1 and to the right and up 1 to the left. And then the next one down here would be at -8 from there. That's 1, 2, 3, 4, 5, 6, 7. Be somewhere down here. Okay? And this one up here would be +8 from here. 1, 2, 3, 4, 5. Yeah, we still are off scale. So it's something like this. Okay. Do you see how we got that? Okay. Start with the cubic function, negate it, which flops it over, okay, and then add 2 to that. So that got us here. That's where we're starting. Why is it doing this? Okay. I guess because it wants to. Okay. Now we're going to do a g of x. I need a color. What color should g of x be? Blue? Light or dark? Say? Light. Okay, that's Carolina blue, by the way. I was born there. Okay. All right. G of x, can you see that? Okay. Is equal to f of 2x. Okay. What are we doing here? What are we doing? Which variable are we adjusting? The horizontal variable or the vertical variable? The which? X is the vertical variable, huh? Okay.
No, it's horizontal.
No, it's a horizontal variable. So what are we doing when we multiply by 2? A what? Okay, we would be, except it's the horizontal variable. That's taking half. Remember, anything dealing with the x is reversed. So normally with a y, that would have been stretching, but this is compressing. So that becomes a horizontal shrink by 2. Okay? So guess what? 0, 0 remains 0, 0. But 1, 2 becomes 1/2. I'm sorry, 1/2 2. I put it in the wrong place. Okay? Let's erase that one. Okay. Okay. It was 1, not 2. Okay, sorry about that. Pin back. Okay. This one, when we're at -1, 3, it goes -1, just half of that. Okay? Right there. No. It's half of -1. I'm sorry, I did it backwards again. Okay. Go half and then 1. Okay. All right. And the next one would have been way down here somewhere. So what it's doing is, well, it should be closer in. This should be halfway all the way down, and this halfway, I got that closer all the way up. Because it's a horizontal shrink by half. Shrink by 2. Okay? Now, it sort of looks like a vertical stretch, but it's not. It's a horizontal shrink by 2. Did everybody see that?
I see it, but it's like, how did you get the points? Like,
Okay. Okay. This point, half of 0 is 0. Okay. That didn't check. I mean, okay. Horizontally, it was a 0, 2. You do half of the x value, half of 0 is 0, it stays 2. Okay, this was a 1, 1. Okay, it just turned out being a 1, 1. So this will be a 1, and I mean a 1 half, but keep the same y value, 1. This one was a negative 1, 3. So this will be a negative 1 half, 3. You take half of the x value, but keep the y value exactly what it was. Okay, so that's what you're doing. The next one down here would have been somewhere. We might could have gotten that on. Let's see. 1, 2, 3, 4, 5, 6, 7. Yeah, almost. Yeah, that would have been 1, 8, right down there. It would have been over this way some. And this one would have been, that wouldn't show up. Okay. That's right, it's a horizontal shrink. So let's go with H. What color you want H to be? Help me, somebody.
Yellow.
Oh boy, yellow. Okay, this is going to be a little hard to see, but if you can't see it, I'll change it. So here's our h of x. Can you see that? Yeah, it shows up okay, doesn't it? Okay, it doesn't show up well on my screen, but it's better on the board. Is equal to 1/4 of x squared. No, wait, I'm looking at the wrong one. Sorry. I was looking at the check yourself. I said, that's not what we're doing here. Okay. Do my h of x again. F of 1/2 x. Or x over 2, you could have said. Okay, what you reckon is happening there? I hate it when people leave the lids off pens. That was a brand new looking pen. It's now a dry pen. Say again?
Horizontal stretch.
It's a horizontal stretch. Horizontal because you're messing with the x, and stretch because you go in the opposite direction. This is a small number, so stretch. By how much? 2. Okay. So this is a 0, 2. Double 0, you're still 0. So 0, 2 stays right there. So that's not a surprise. Okay. But this one, you go back to the original, F. This was 1, 1. You double the x and make it 2. Leave the y the same. 2, 1. So that doubles out to here. Okay. 2, 1. Okay. Back here, this was a -1, 3. You double the x because it's a horizontal stretch to make it -2, but you stay at value 3. Okay. So -2, 3. Okay. The others we can't show here, but they would just be stretched out horizontally like that. And it should be twice the distance here. I didn't quite get that. Twice the distance there. I did better up there. You're going up at twice the rate, stretching horizontally. Does that make sense? Let's see if the book did it right. Oh my goodness, look at them. They did get really close. Okay. Any questions? And there's a checkpoint with this one, so I really highly recommend you do those. Okay, that finishes 1.7. We almost are out of time. Let's quickly do our vocabulary here. Horizontal shifts, vertical shifts, and reflections are blank transformations. Rigid, perfect. Number 2, a reflection in the x-axis of a graph y is equal to f of x is represented by h of x equal reflection in the x-axis. Any guesses? Any guesses? H of x equal reflection of the x-axis flips it over, right? So what was positive becomes in y. So what's your y?
Negative.
Yeah, but what is your y? Most important thing in the course, f of x. So that would be where h of x is equal to negative f of x. Negate the y. That's reflection across the x-axis. Okay? And while a reflection in the y-axis of y is equal to f of x would be represented by h of x equal, no, f of negative x. You're right. F of negative x. That's reflection across the y-axis. Perfect. Number 3, a non-rigid transformation of the graph y is equal to f of x by g of x equals c times f of x is a blank blank when c is greater than 1.
Vertical stretch.
Vertical stretch, excellent. When c is greater than 1, and a blank blank when c is between 0 and 1. Vertical shrink, you got it. Okay. Number 4. Okay. A lot of you don't have books still, right? Now, I did give you all the codes, didn't I? Okay. What's that? Okay, I can't hear it. A little low. Yes, you can. Good. Guess what? For my trig class, they put intermediate algebra book, not the book, but they put the problems in for that. It makes no sense, so they're trying to fix that. Okay, but I think they can still access their book. They got the book right anyway. Okay, so let me write these. Let me write them in dark. Okay, h of x equal f of x plus c. What's that?
Right.
It's what?
Going right.
Okay. What is your f of x?
1.
Y, and you're adding something to it? So what are you doing? Up. That's a vertical translation upward. Okay? C units up. That would be Roman numeral 4 if you're doing it in your book. H of x is equal to f of x minus c. We're assuming c is positive, by the way. What's that? Vertical shift down. That would be Roman numeral 2. H of x equal f of x plus c, horizontal left, and h of x equal f of x minus c. Horizontal shift to the right. Perfect. Homework exercises. Do 5 or 7. They both should be at calcchat.com. Do 9. That should be at calcchat.com. Do 11 or 13 or both. They both should be at calcchat.com. Do any of the odds 15 to 19. They should all be at calcchat. 15's at calcview. Do any of the odds 21 through 37. That's a lot of them. They all are at calcchat. 21's at calcview. Do any, okay, now get this, folks. That group I just said, 21 to 38, that's given the function, you write what the changes are doing, okay? In the next group, 39 to 47, they write what's happening, you give the function. So you see it's doing it one way and then the other way. So do any of those 39 to 47, or 39 to 45, they're all at CalcChat, 39's at CalcView. Then do 47, I say either 47 or 49, they both should be at CalcChat. Then do any of the odds 51 through 55. They should all be at CalcChat. And then do either 57 or 59. They should both be at CalcChat. There is a 61 that looks pretty interesting, so you can do that if you're interested, especially those who may be going into engineering, especially, say, mechanical engineering. That would be a nice problem there. True false, either 63 or 65. They should be at CalcChat. And then 67 is finding points on a graph. That should be fairly straightforward, I think. Error analysis, I don't really care for that much, but you can do it. It will teach you something. That's 69. 71 is describing profits. That sounds good to me. That's 71. And that's all, folks. We'll start next time at 1.8. Okay. Good deal. Any questions? Good deal. Have a good day. We'll see you on Thursday.